Hi and welcome back to today's video. In this video we're going to talk about basis transformations. You will hopefully remember that we've talked about matrix representations for linear mappings, and you'll also remember that the matrix representation depended on the choice of coordinate systems. So once we choose a basis for the domain or the codomain or both, we can compute the matrix representation of any linear mapping. And the actual numbers in that matrix representation will change if we change the basis or the coordinate systems in domain and or codomain. Now, the task that we're going to look at in this video is the question of how to represent that change of basis, this basis transformation. So this is the topic of today's video, basis transformation. Before we go into details on basis transformation, let's first have a look at how matrix multiplication works, what matrix multiplication represents for matrices representing linear mappings. As it turns out, multiplication of these representative matrices is equivalent to concatenation of the respective linear mappings. So that's our first theorem for today. It's going to look a little abstract, but it's actually not very complicated. We want to start with two linear mappings, and for those we need three finite dimensional vector spaces. One as the domain for the first linear mapping, one is its codomain. That codomain is going to be the domain of the second linear mapping, and then we need a third vector space as the codomain of that second linear mapping. So we just call those x, y, and z. Let x, y, and z be finite dimensional vector spaces. And we have linear mappings. We have a linear mapping F with X as its domain that maps to Y. And we have a linear mapping G with Y as its domain that maps to Z. So those are linear mappings. And furthermore, we need coordinate systems for all of our vector spaces so that we can compute matrix representations. We'll call those Bx, By, Bz. And those are coordinate systems for x, y, and z, respectively. Then we can take a look at the composition of G and F. And in that setting, F starts at X, the codomain is Y, and G starts at Y. So we can first do F and then apply G to the result. So we have to look at G after F. So that here means G after F. That means apply F first, then apply G. So you have to read this from right to left in a way. Okay, so that mapping that has the domain X because F is applied first. The intermediate result is in Y, and then G is applied, so the end result will be in Z. That means that mapping has Z as its codomain. This is, of course, linear. Composition of linear mappings is always linear. That's not that hard to see. What is more interesting is what about the matrix representations of these linear mappings? Now, if you want to have the matrix representing the composition of G and F with respect to these two coordinate systems, Bx and Bz, we can obtain that using the matrices that represent F and G. And basically, that new matrix can be obtained as a matrix product of the old matrices, where the order of the matrix product is the same as the linear mappings here. So what we need to do is we need to write the matrix representing G on the left and then representing F on the right. And of course, the coordinate systems need to be compatible. So we want to input a vector with respect to Bx here. So we need that input here on the right for F. The output here is then in the coordinate system By, and G takes its input in that same coordinate system. So those two, of course, those have to be the same. And finally, the output is in Z, so we use the coordinate system Bz, and that same coordinate system has to be used here for the output. So the idea is the input into that mapping here, you put that into F, it's being processed, then the result goes into G, then it goes out. That's the final result. And the same happens for the matrix product. So if you have a vector that you want to pass into that mapping, you multiply it here on the right. It first gets multiplied with this matrix representing F, and then it gets processed by the matrix representing G, and the output is in Z coordinates. So if you look at this in a diagram, basically that looks like this. So we first have our mapping F that we apply, then on top of that the mapping G. And in the coordinate spaces, the corresponding coordinate spaces, here we have the coordinate system Bx, here we have By, here we have Bz, and the corresponding spaces and basically what the mapping between those two coordinate spaces is then given by the matrix that represents F with respect to Bx and By, and the mapping here that represents G with respect to By as the input and Bz as the output. So this here is in a different order than up here, unfortunately. Right? So you can see we're going from the space Y to the space Z, from coordinates By to coordinates Bz. But with a matrix, we write the input on the right and the output on the left. And the reason for that is that if we want to actually process a vector using that matrix, then we multiply that vector on the right, and here we have the input and the output is on the left. So that's compatible with this definition here of matrix multiplication. Okay? So now that is a very fundamental theorem for matrix representations of linear mappings. And of course, we can use that to come up with a matrix transformation. So the idea here is now the following. If we have a matrix that represents a linear mapping with respect to a given coordinate system, and we want to change the coordinate system, then we can do this in 2 or 3 steps. We can first change the coordinate system, then apply the matrix we know, then change the coordinate system once again. And that's what we're going to do now. So sum up this idea. Let's say we have a vector given in some coordinate system. So if a vector is given through its coordinates in a coordinate system, let's call that B. And we want its coordinates in a different coordinate system, B bar. And we want to obtain its coordinates with respect to a different system we call B bar. How can we compute that? How to compute that coordinate transformation? The idea is pretty simple. We are looking for a mapping that does not change the vector itself. We only want to change the coordinate system. And of course, there is such a mapping, and that's the identity. The identity map just outputs the same vector that is in the input. So if you give a vector to the identity map, it outputs the very same vector. And of course, we can use that identity map, and we can compute a matrix representing that identity map, and use then different coordinate systems for the input and the output coordinate system. We use B as the input system, B bar is the output system, and there we have a matrix that does exactly what we want. So we need a mapping that does not change the input vector. That is the identity mapping. The identity is usually denoted by id. It's defined for any vector space V. It maps back to V, and id of any input V is exactly the same as the input V. So that identity mapping is, of course, linear. And that means what we can do is we can find a matrix representation for that. And we just incorporate the change of bases, the change of coordinate systems in here. We want an input B and an output B bar. And that means if we have this vector given in B coordinates, and if we multiply matrix representation of id times that vector, then we'll get back the same vector, but in B bar coordinates. So that's exactly the change of coordinates that we want here. And this matrix is what we call a transformation matrix, or a basis transformation matrix. So that's going to be a definition, that name. So again, let V be a finite dimensional vector space, as always. And let ID V to V be the identity mapping on V, meaning id of V equals V for all V in capital V. And let B and B bar be coordinate systems on V. Then the matrix, and that matrix is often denoted by a T for transformation. And again, we just write the bases of the coordinate systems as indices here. So as usual, this here is the input system, and this here is the output system. And that is defined as the matrix that represents the identity map with these two coordinate systems as input and output. So this matrix here, that is called the basis transformation, or just transformation matrix. For the transformation, from B coordinates to B bar coordinates. And as a quick note here, this matrix is of course invertible. You have bases on both sides and transform from one basis to the other basis. So you can of course revert that procedure. And the inverse of a matrix is exactly the matrix where you exchange the two coordinate systems. So if you do the reverse coordinate system transformation, then of course that will undo the effect of transformation. So that means a matrix like this, TBB bar, is invertible with TBB bar inverse being exactly TB bar B. So you exchange these two, and that's the inverse of the original transformation matrix. In other words, you only have to compute one of those transformation matrices. The other one is then just the inverse. You'd have to compute the inverse of that. So what does that mean for our linear mappings and for the change of bases in linear mappings? Well, we just need to plug those two results that we have together, and we get what we need here. So for any linear mapping f from V to V, let's start with V to V, on a finite dimensional vector space V, and coordinate systems, we call those B and B bar again, on V, we have the following. Let's say we want to compute the matrix that represents F with respect to B bar. And we have the matrix that represents F with respect to B. Maybe F is given that way, or it's easy to compute that one, but we actually want the representation with respect to a different coordinate system. How do we do that? Well, what we have here, let's write this out. So we have a B bar here and a B bar here, and we have B and B here on both sides. What that means is the input vector that we want here is a vector x in B bar coordinates. And the output is again a vector f of x in B bar coordinates. So that's exactly what we want. How do we get that? So here we also need to have f of x in B bar coordinates. Here the output of this operation here will be necessarily f of x in B coordinates. So To get from B to B bar coordinates, of course, we need to add a matrix transformation. So we need to add this transformation here. We need to take the result of this matrix here and transform it to our basis B bar. And similar thing on the right-hand side here. What we want here as an input vector is a vector x in B coordinates. What we have here is a vector x in B bar coordinates. And now, of course, we need to transform that first. So we need to take this B bar vector and transform it to B. So this is the chain that changes our basis, our coordinate system on both sides. We start with B bar. We first transform to B. Then we apply the mapping with respect to B. We get an output in B. And then we transform that to B bar. And altogether, that's the same thing as applying the mapping to a B bar vector and getting a B bar vector. So these two are equivalent. And that means if we have this matrix here and want this one, then we just have to add these two transformations. And of course, you could also say this is the same thing as T B bar B inverse times FBB times T BB bar. Okay, that was pretty abstract, probably. Let's have a look at an example before we actually go on. So here's an example of how this is working. Let's say we have a matrix A that's defined as 1 over 10 times 8, 1, 2, 9. And we define a linear mapping F from R2 to R2 is defined as f of x equals a times x. So A is the matrix representation of F with respect to the standard basis. And the standard basis is, of course, 1, 0, 0, 1. Okay, so F with respect to the standard basis, that's exactly A. Now let's say we wish to compute the matrix representation of F with respect to a different basis. We call that basis B. And B, let's say B is 1, 2, and 1, minus 1, just as an example. So those numbers are arbitrary for the moment. How do we do that? The first thing we need is the basis transformation. So we want a basis transformation matrix, and we compute the basis transformation matrix that transforms from B to C. Why we choose that and not the other one will be obvious in a minute, I hope. So how do we do that? Well, we need to take our vectors in B, and we need to compute the images of those vectors. So in other words, what are the images of those vectors? Well, let's take the first vector, 1, 2. You want the image of 1, 2, and we want that under the identity map. and we want it in C coordinates. Well, what is the image of 1, 2 in C coordinates? Well, 1, 2 is mapped to the same vector using the identity map. And the C coordinates of 1, 2, we get those if we try to represent that vector as a linear combination of the basis vectors, 1, 0 and 0, 1. And of course, that is 1 times 1, 0 and 2 times 0, 1. So that means the C coordinates of that vector are exactly 1, 2, same as the vector. And that's a neat thing here. And secondly, we'll also need 1, minus 1, and again, that maps to that same vector under the identity map. And the coordinates of that vector are, of course, 1 and minus 1 with respect to the unit basis C. So what we get here is the C coordinates of that vector are exactly 1, minus 1, same as the vector. And remember, the columns of the matrix representation are the images of the basis vectors, of the input basis vectors in output coordinates. So we already have these. Those are the images of the basis vectors of B in output coordinates, in Z coordinates. So we can write down that matrix already. So that means what we get here is the transformation from B to C, that is the matrix representation of the identity from B to C. And that is exactly 1, 2, and 1, minus 1. Like this. So that's what we want. So here we have our transformation matrix. And just as a side note, I was saying that the C coordinates of these vectors here are exactly the vectors. You might wonder what their B coordinates are. So just as a quick side note here, what if we wanted to compute the B coordinates of one of those vectors? Well, then we'd have to take the basis B, these two here, and represent that vector as a linear combination of that basis B. And of course, what we get here is we need exactly once this vector and 0 times the other one. So the B coordinates of 1, 2 are 1, 0. And of course, that same is true for 1, minus 1. If we look at the B coordinates for that, we need 0 times the first vector and 1 times the second one. So the B coordinates would be 0, 1. And if you look at that, well, what happens if you input one of those B coordinate vectors to the transformation? That's exactly what we wanted. So if we take this matrix here, the transformation from B to C, input a vector in B coordinates like 1, 0. That's B coordinates for 1, 2. Then what happens here is we get 1, 2, 1, minus 1 times 1, 0, and the result is 1, 2. And that is C coordinates for 1, 2. So the transformation does exactly what we want here. Okay, so that just as a side note. Of course it does what we want. That's how we constructed it. Okay, so now we have this first transformation matrix. Of course, we also need the other one. That's going to be our second step. We also want to compute T from C to B. And we know this is the inverse of the matrix that we already have. So we just need to invert that. You will hopefully remember the formula for inverting 2 by 2 matrices. If not, let me show that to you. So the inverse of a 2 by 2 matrix of that form here is given as 1 over the determinant of that matrix times, and now what you do is you exchange the elements here on the diagonal. So the D comes on the top left and the A goes to the bottom right. And for those not on the diagonal, you just change the sign. So here we get minus C instead of C and minus B instead of B. That's the formula for the inverse of the 2 by 2 matrix. Of course, if you don't want to remember that, you don't have to. You can always apply the usual inversion procedure. But in this case, it might be convenient to use that formula. So we do that. And that means the inverse that we get is 1 over the determinant of 1, 2, 1, minus 1 times, and we exchange the diagonal elements. That's minus 1, 1 here, and we put a minus in front of the non-diagonals, so it looks like this. Now the determinant, that is minus 1, minus 2, so that's minus 3, so we get minus a third times this matrix here, and we can simplify that a little. So that's a third times 1, 1, 2, minus 1. We factor a minus out of the matrix, and then that cancels out with minus 1 over 3. Okay, so now we have those two matrices that we want, and now we can finally determine our matrix representation with respect to B, because we know that matrix representation is going to be that with respect to C. We know that one. And then we have to add transformations. So before, so on the right hand side, we transform from B to C. Then we apply this mapping here. And then we have to transform back from C to B. So here's this one. And we now all have these matrices here, so let's write those down. First one, the transformation from C to B, remember, that is this one here. So that's 1 over 3 times 1, 1, 2, minus 1. Then this matrix, that was our original matrix A. A was given as 1 over 10 times 8, 1, 2, 9. And finally, this transformation matrix here is the first one that we computed. That was this matrix here. 1, 2, 1, minus 1. So what do we have to do now? Well, we just have to compute this matrix product. Let's see. 1 over 3 and 1 over 10, we can take both of these out. That's 1 over 30. We copy the first matrix and we compute the product of the last two of these two here first. And what we get is, let's see, 1 times 8 plus 2, that is 10. Then we have in the second row, we have like this row times this column. So that's 2 plus 18, that's 20. Then we have first row times second column, that's 8 minus 1, so that's a 7. And finally, we have this row times this column, so that's 2 minus 9, that is minus 7. And then let's multiply those two matrices here. First row is, there's 1, 1 times 10, 20. That's 10 plus 20, so that's 30. the second row, 2 minus 1 times 1020, that's 20 minus 20, that's going to be 0. Then first row, 1, 1 times the second column, 7 minus 7, that's 7 minus 7, that's 0. And finally, the second row, 2 minus 1 times the second column, that's 14 plus 7, that is 21. So the matrix that we get here is 1, 0, 0, and then we have 21 over 30, that's 7 over 10. Like this. So you can probably see why I chose that specific basis here for the transformation, because the matrix now is in diagonal form. And of course, that's much neater to do computations with. So this new coordinate system B has a nice property with respect to my linear transformation. The linear transformation, the F, can be represented by a matrix in diagonal form here. So that means we can nicely isolate the effects that F has on the two coordinate directions. Of course, those are not the standard unit vector coordinate directions anymore. But in this new coordinate system, it's very easy to represent the mapping, and it's very easy to work with that mapping in the new coordinate system. So once we have transferred everything in that system, it'll be much easier to work with our matrix. And we'll see some applications in the exercises for why you would want to do such transformations. We'll go a little deeper into that topic in the next semester in Math 2. And then we'll be discussing how to actually obtain such a basis. So in this case, you remember I gave you that basis B. That just was an arbitrary basis I selected. Of course, you can now see it was not that arbitrary after all. I carefully handpicked that basis. And of course, the question is, how can one do that? And we'll discuss that question next semester when we'll do Math 2 and talk about eigenvalues and eigenvectors. That's an interesting deep theory in connection with these matrix representations. But unfortunately, we will not be able to cover that this semester. So that concludes our discussion of basis transformations. And I, of course, hope to see you in one of the upcoming videos. Goodbye.